The next AMOS application we'll explore is the Online Boutique, originally developed by Google Cloud Platform as a reference implementation. This application is widely used to demonstrate modern microservice architecture in action. What makes the Online Boutique especially well-suited for AMOS is its fully containerized design and its rich diversity of services, languages, and communication patterns. Each component, whether it's handling user interactions, managing carts, processing payments, or placing orders, operates as an independent service, yet must work together as a coherent whole. By running the Online Boutique through AMOS, we're able to observe how a complex microservice application behaves as a living system. AMOS does not simply deploy these services, it monitors their interactions, records events, and responds dynamically to changes in the environment. This allows the application to adapt, recover, and maintain stability even as individual services fail or restart. In this video, we'll walk through how the Online Boutique operates within the AMOS ecosystem, and how AMOS transforms a traditional microservice demo into an adaptive, self-regulating system. The Online Boutique application is open source and publicly available on GitHub, which makes it an ideal candidate for experimentation and system-level exploration. Rather than building a custom demo from scratch, we start by pulling the application directly from its source repository. This demonstration shows how it is possible to easily migrate existing containerized solutions into the AMOS ecosystem. By pulling the application from GitHub, we preserve the original structure and intent of the system. Nothing is simplified or rewritten to fit AMOS. Instead, AMOS is designed to adapt to the application as it exists, ingesting its services, configurations, and dependencies as first-class entities. At this stage, the Online Boutique is still just a collection of source code and service definitions. In the next steps, we will design the application schema, interpret these services within AMOS, deploy them as a connected network, and observe how they behave once they come alive. The AMOS architecture treats each containerized service as part of a living system. Services are deployed as a distributed application using Docker, connected through a virtual private network, and modeled in a graph database. This combination allows AMOS to understand not just where services run, but how they relate, communicate, and evolve over time. The next step is to model the application structurally inside AMOS. We do this by defining a tiger graph schema that mirrors the services, connections, and behaviors of the running system. This schema is defined using a YAML specification that describes each service as a vertex in the graph. Every major component of the Online Boutique, such as the front-end, checkout service, cart service, product catalog, and payment service, is represented as its own vertex type. These vertices don't just identify the services, they capture operational state, deployment details, network configuration, and health information. Each vertex includes attributes like the Docker image and tag, the service's role, its deployment and public URLs, exposed ports, and health check endpoints. This allows AMOS to treat infrastructure details and runtime state as graph data, rather than external configuration scattered across files and scripts. At the center of the schema is the AEM, the Application Event Manager. Every service in the Online Boutique is connected to the AEM through a dedicated edge. These connections allow AMOS to observe, record, and respond to events generated anywhere in the system, forming the sensory layer of the application. In addition to event connectivity, the schema also captures the application's business logic through directed edges. These edges reflect how services communicate at runtime using shared knowledge from the schema. By representing each process as an existing Docker container and capturing both event awareness and service dependencies in the graph, AMOS forms a complete, living model of the application. This schema becomes the foundation for deployment, continuous monitoring, autonomous recovery, and adaptive behavior. In the next section, we'll see how AMOS uses this schema to bring the online boutique to life as a connected, observable system. In the source code, we can build the Docker images and then turn toward AMOS for deployment. Using the APM, we submit a deployment YAML file for the online boutique application. This YAML defines the Docker image for each service, the CPU and memory resources, the exposed ports and protocols, and the network each service joins. At the top of the file, we define the target execution environment, the cluster name, region, and security settings. This is what allows AMOS to deploy the application consistently into a real distributed runtime, without hard-coding infrastructure decisions into the application itself. We also define the graph name, which is where AMOS will record services, relationships, and runtime events as the system operates. The key architectural idea in this YAML is how AMOS introduces the AEM directly into the communication fabric of the application. Instead of services calling each other directly, the front-end and other upstream services are configured to route their downstream requests through the AEM using the same ports they would normally use. Inside the AEM configuration, the routes setting defines exactly where those proxide calls should go, mapping each incoming port on the AEM to the real destination service and port. This turns the AEM into an observer sitting in the middle of the system. It sees the traffic, records events, and can enforce policies or trigger responses, while the application still behaves like a normal microservice architecture from the perspective of each service. This YAML also standardizes operational behavior across services, things like health checks, log groups, and desired replica counts, so AMOS can deploy, monitor, and recover the system using the same configuration source. In other words, the YAML isn't just deployment metadata. It's the contract AMOS uses to treat the online boutique as a living, measurable, and controllable system. With this YAML file submitted to the APM, we can now deploy the application. As the deployment is processed, each service appears in the graph as its own vertex, with edges representing the communication paths between services. Once the application is running, the graph begins to reflect live behavior. As we visit the front-end service and interact with the online boutique, we can watch container-to-container communication unfold. Requests flow through the system, events are recorded, and relationships update dynamically as users move through the application. At this point, the online boutique is no longer just a microservice demo. It has become a living system within AMOS. What began as a collection of independent containers is now a fully deployed, observable, and adaptive application whose structure and behavior are continuously reflected in the graph. Through AMOS, we gain visibility not only into where services are running, but how they interact, how they respond to change, and how the system maintains stability over time. Failures are no longer opaque events buried in logs. They become first-class signals that can be observed, reasoned about, and acted upon in real time. This is the core shift AMOS introduces. Instead of treating deployment, monitoring, and recovery as separate concerns, AMOS unifies them into a single graph-driven model of the application. The online boutique doesn't just run, it senses, adapts, and evolves as conditions change. While this video focused on a familiar reference application, the same approach applies to any containerized system. AMOS is designed to integrate with existing architectures, preserve their intent, and elevate them into adaptive, self-regulating systems.